Hello, everyone. We're going to talk about a couple tests that we use to analyze infinite series. They're called the limit comparison test and the ratio test. So the big question that we've been talking about for a few classes is how to know when an infinite sum converges. And a few things that we've seen along the way are, first, we define an infinite sum to be the limit of a sequence of partial sums. And then we have the result that every bounded monotonic sequence converges. And so we apply this idea to our sequence of partial sums, and in particular, if we have positive terms, then our sequence is increasing. That's one type of monotonic sequence. And so by the second result, we only need to show that the sequence of partial sums is bounded, and then we've shown that the series converges. So these were all things that we talked about last week, and one of the ways we applied this is in the comparison test. So in class, we talked about this. We can compare our new series with a familiar series. If we can set up an inequality between the terms like this, then we can say that the new series converges. But it turns out there's an easier way to analyze this. We mentioned this briefly at the end of class. We don't actually need to look at all the terms of the series. We only need to look at their behavior as j goes to infinity. And so what we're going to talk about now is the limit comparison test. And here we compare two series, but we compare their long-term behavior instead of comparing all the terms in the series. Here's the limit comparison test. So we have two series, a sub j and b sub j. Both of them are positive. And then we're going to define the following limit. So it's the limit as j goes to infinity of the ratio a sub j over b sub j. One of the series in this ratio is going to be our comparison series, something that we're familiar with, and the other one is going to be the series that we're trying to analyze. So there are three possible cases we can have for the value of this limit L. First, L can be some finite positive number, and in this case, either both of our series converge or both of them diverge. The second case, if this limit is 0, and the series that we put on the bottom of the fraction converges, then the series on the top also converges. There's a final case, so if the limit is infinity, and we know that the series on top diverges, then that proves that the series on the bottom also diverges. Okay, notice the order that we're putting the series into the fraction in cases 2 and 3. That's going to be important when we do a couple examples. The limit that we're trying to find, L, it's comparing the relative growth rate of these two series as j goes to infinity. And if this limit is 0, the terms on the bottom are getting bigger much faster. If L is infinity, it's the terms on the top that are getting bigger. And so this is why we have to set up those last two cases the way that we do. If the limit is a finite number, the two series grow at the same rate and they have the same convergence behavior. When we set up this test, we need to have a comparison series, and that's going to be something that we're familiar with, like a geometric series or a p-series. When we put our comparison series into the ratio, we have to use the ideas based on 0 and infinity. If we're comparing to a convergent series, we have to put that series on the bottom of the fraction. If we're comparing to a divergent series, then our familiar series is going to go on top of the fraction. Okay, let's take a look at this test. Let's look at an example. Here's the first one that we're going to do. So we're looking at the series sum from j equals 1 to infinity, j squared over j to the 5th minus 2j to the 4th plus 5. Whenever we're looking at a problem of this type, our first step is always going to be applying the divergence test. So we're going to take the limit of the individual terms. If that limit is 0, then we're not sure what happens. We need to find another test. If it's not 0, then we're done. We know the series diverges. Here's the limit that we need for the divergence test, the limit of the terms as j goes to infinity. And we know that in a problem of this type, we're going to factor out the highest powers. So on the bottom, I factored out j to the 5th. Now I'm going to cancel powers of j on the top and bottom of my fraction. And what I'm left with, I can replace some parts of this fraction with 0. So those little pieces with j on the bottom got replaced with 0, giving me a limit of 1 over j cubed. And that too is 0 as j goes to infinity. That's the result of the divergence test. If that limit is 0, then it's inconclusive. But notice that along the way, our very last step, we showed that the terms of this series are similar to 1 over j cubed in the limit as j goes to infinity. Okay, that was my last step on the slide before this one. So that gives us the series that we're going to use to set up the limit comparison test. I'm going to use the summation from 1 to infinity of 1 over j cubed, and I'm going to put that into the limit comparison test as my comparison series. All right, what do we know about this series? This is a p-series with p equals 3. This is something we talked about in our last class. We know this series converges since p equals 1. We showed that in class using the integral test. All right, so our comparison series is a convergence series. Remember from our setup, that means it's going to have to go on the bottom of the fraction when we set up the limit comparison test. The new series in this example goes on top of that fraction. Okay, so here's the setup for the limit comparison test. Remember, for a convergent comparison series, the familiar series goes on the bottom and the new series goes on the top. I put in the formulas for those two series here in the fraction. Remember, our familiar series is 1 over j cubed. I put that on the bottom. Now we're going to simplify. Okay, so here's the rule for division of fractions. And then I multiply through to get the following expression. Now when we take a limit like this, we're always going to divide out the highest power of j. I did that here, and then this fraction is going to simplify down to 1. What does this mean? Okay, by the limit comparison test, if our limit is a finite number and the comparison series converges, then that means that our new series is going to converge as well. All right, remember, even though we know that this series converges, we don't know anything specific about its value. That's a different question. We would do that using a computer, and that was the problem that you did for your last programming project. That was last week in class. All right, that's one example of how we use the limit comparison test to analyze a series. Let's do another example. This one's going to be a little bit different. It has a square root, so our steps are going to change. Whenever we're analyzing the convergence of a series, we always want to start with the divergence test. So I set that up here. I'm looking at the limit of the individual terms. Similar to our last example, we're going to factor out the highest power. Then we cancel on the top and bottom. And when we put in 0 for that 1 over j cubed, we're left with the following limit. I can simplify the square root in this expression, so I get just 1 over j. And that limit is in fact equal to 0. Again, just like our last example, the divergence test is inconclusive, but we're going to use our final step to come up with a comparison series. So the limit that I got on my last step was the limit of 1 over j. I'm going to use this series, summation j equals 1 to infinity of 1 over j as my comparison series. Remember, this series has a special name. It's called the harmonic series. We did a proof in class, 2 proofs actually. We showed that the harmonic series diverges. And for a divergent series, we set up the limit comparison test with the familiar series on top of the fraction. There's the setup for the limit comparison test. My familiar series is 1 over j, so that goes on top. And then the new series we're trying to analyze goes on the bottom. Okay, before we start canceling, we have to deal with the square root. So I want to use some of the properties of square root that we learned in algebra class. And my first step, I need to rewrite the top of my fraction also as a square root so that it matches the bottom. I did that here. Now I'm going to use the rule we know from algebra. If we're dividing 2 separate square roots, we can combine them. And we do the division under a single square root instead. Okay, next I have my rule for dividing fractions. And then I multiplied everything through and got the following result. We can cancel out our highest powers of j, and then we let that 1 over j squared go to 0. And we get the answer 1 for this limit. In the problem we're looking at, we calculated the limit and found that it was a finite number. We were comparing our new series with a divergent series, and so we conclude that our new series also diverges. That's the limit comparison test. The other thing that we're going to talk about is the ratio test. So when we use the limit comparison test, we set up a fraction. It had terms from 2 different series. In our next test, we're also going to set up a fraction. This time it's going to have 2 terms from the same series. So let's take a look at the ratio test. Like our other tests so far, this applies to series with positive terms, and we're going to define the following ratio. So it's the limit of the ratio a sub j plus 1 over a sub j. We have a few possibilities. First, if this ratio is less than 1, the series converges. If it's greater than 1, the series diverges. And finally, if it's equal to 1, the test is inconclusive. So we're going to need to use another method to find the convergence in that case. If we wanted to prove the ratio test, well, we'd have to do that by looking at the different cases separately. And for the cases we would use a comparison test, we compare with a geometric series. So the ratio that we saw on the last slide, that's familiar. We had that same ratio when we analyzed convergence for a geometric series. We're going to come back to this idea in class, but now I want to look at a couple examples. Here's our first one. In order to set up the ratio test, we're going to need formulas for 2 terms in the series, 2 subsequent terms. In this example, we have on the left a formula for a sub j. On the right, we have the formula for a sub j plus 1. Notice that when we set up the factorial, we have to put the j plus 1 in parentheses. Now I'm going to plug these formulas into the limit that we're calculating, the ratio r. Here's a setup, putting in the formulas that we just talked about. Then I use my rule for simplifying fractions. And the next step that I'm going to do involves the factorials. So I'm going to write those out in expanded form. I'm doing this to make it clear what cancellations we have on the top and the bottom. If you look at that, you see that most of our factors from those factorials are going to cancel out. That leaves me the following expression. And when I take the limit of this fraction, I get 0. Well, now we have the answer to our problem. The ratio that we just calculated is less than 1, and so the series converges. I want to take a look at a second example. So here we have the series where the terms are j to the power j over j factorial. I'm going to use the ratio test, so here's the setup. And then this is what I calculated for the two terms that I need out of my series. The rule for simplifying fractions. Okay, and then I multiplied through, combined everything into one fraction. My next step, I'm going to expand the factorials again. Now I look at which factors are going to cancel on the top and bottom. I get the following cancellation, but I can actually go one step farther. Notice that the two parts of this fraction share a common factor of j plus 1, so I canceled that out on my next step. Okay, I rewrote it so that everything was raised to the power j, simplified what was inside, and that limit is equal to e. We talked about this last week in class. If you wanted to go through the steps, you would need to use a log to find that answer. What do we learn from the ratio test? Well, in this example, the ratio, it's e, which is about 2.7. That's greater than 1, and so the series that we're looking at diverges. I have a couple problems I want you to try for our next class. That's it. Thanks.